Good morning all. In this lecture, I will explain what are the possible spectroscopic terms arising from two valence electrons. So, first we will consider the ground state of a two electron system, that is a system which have two valence electron. The simplest case is helium 2. The ground state electronic configuration is 1s2. You have 1s orbital here and two electrons are there. According to Pauli exclusion principle, they will fill like this, one with upspin and the other with downspin. This is the ground state electronic configuration of helium 2. Here the first electron have s value half and the second electron have minus half. Actually these s1 and s2 are the ms values. Okay, I will denote these simply by s. Okay, so the first one have ms value half and the second one will have ms value minus half. Okay, so the total ms value, all these ms, from now on I will denote it as simply s. So the total s value will be sigma si. There are two values, so if you add these two you will get 0. What about ml values? Again I will denote this as L1 and L2 for the two electrons. For the first electrons, since it is in the 1s orbital, L value is 0, so ml value is also 0. For the second electron also it is in the 1s orbital, so L value and ml value are 0. L1 0, L2 0, total L value is sigma Li and it will be 0. So capital S is 0, capital L is 0 and J is simply S if you are considering a half filled or fully filled orbital. In the case of ground state term symbol, when you are writing J, if it is a fully filled orbital or a half filled orbital, J will be simply S. And if it is a less than half filled orbital, J will be modulus of L minus S, and if it is a more than half filled orbital, J will be modulus of L plus S. That is the rule for writing ground state term symbol. Okay, and the term symbol notation is 2s plus 1 Lj. Instead of L, if L is 0 you have to write S, if L is 1 you have to write P, if L is 2 you have to write D, if L is 3 you have to write F, and so on. So 2s plus 1 Lj becomes 2 into 0 plus 1, that is 1. Since L is 0 you have to write S and J is simply S and it is 0. So 1s0 is the ground state term symbol for helium 2. Helium 2. Now what happens for the excited state? What are the possible excited states? There are different excited states, and we will consider the first case. Among the two electrons, one electron excited to 2s orbital. That is, now the configuration is one of the electron is in the 1s and the second electron is in the 2s state. Okay, that is the lowest possible excited state. That is, now we are having two s electrons, one at 1s orbital, the other one at 2s orbital. Therefore, S1 will have a value half, S2 will have a value half. I am not writing plus half or minus half. Both these can be plus or minus, because in the excited state it is not going to obey this Pauli exclusion principle. Filling is not according to Pauli exclusion principle. This electron which is excited to 2s can be in the upspin state also. Okay, it is not necessarily in the downspin state. When you are writing ground state, if one electron is in the upspin state, the second electron will be in the downspin state. But when you are considering an excited state, the second electron is in another orbital, okay, 2s orbital, so it need not be in the downward spin. Okay, down spin. It can be in the up spin also. So we are taking the general case. S1 is half, S2 is half, and the total S, depending on whether both are in the upspin or one in the upspin and the other in the downspin, it can have values mod S1 plus S2 to mod S1 minus S2. That is, here you can have two values, half plus half. If both are in the upspin or both are in the downspin state, then mod S1 plus S2 becomes 1. If one is in the upspin and the other is in the downspin, it will be 0. So the S value can be 1 or 0. That is the case with the excited state. Okay, in the case of ground state, we can write explicitly what is the total S value, but in the case of excited state, there are two possibilities. Anything will happen, 1 and 0. Now, what about L value? Both electrons are in the S orbital. So for first electron, L value is 0, ml is 0. Second electron, L value is 0, ml is 0. What about total L? That is from modulus of L1 plus L2 to modulus of L1 minus L2. So here it is simply 0. Okay, so we have two possibilities. One is capital S1 and capital L 0. Other one is capital S 0, capital L 0. For the first case, you can have J value 1, because J can in general take values from mod L plus S to mod L minus S. In the case of ground state, I mentioned that if it is a completely filled or half filled orbital, J equal to S, and if it is less than half filled, J is mod L minus S. For more than half filled, J is mod L plus S. But in the case of excited states, J can be from modulus of L plus S to modulus of L minus S. So here from 1 plus 0 to 1 minus 0 means simply 1. Okay, J is equal to 1. Therefore, SLJ we obtained as 1, 0, 1. The term symbol becomes 2s plus 1, Lj becomes 3s1, 3s1. This is one of the possible excited state. The second case is S equal to 0, L equal to 0. Then J can have only one value, mod L plus S to mod L minus S, it is simply 0. Substituting for S, L and J, you will get 1 as 0. So if one electron excited to 2s orbital, then the possible spectroscopic terms are 3s1 and 1s0. 3s1 and 1s0. Suppose one electron excited to p orbital. Okay, the second possibility. That is, among the two electrons, one is in the 1s orbital and the other one is in the say 2p orbital. So it is known as sp electrons, one at S and one at p. Then S1 value is half, S2 value is half, total S value can be 1 or 0. So for any of the excited states with the two electrons, the possible S values will be always 1 and 0. Okay. What about L values? For S electron, L value is 0. For P electron, L value is 1. Therefore, total L value is from mod L1 plus L2 to mod L1 minus L2. That will be 1. 1 plus 0 to 1 minus 0. It is simply 1. Then there are again two possibility, S1, L1. Okay. Then S0, L1. When S equal to 1, L equal to 1, J can have values L plus S to L minus S. That is, L plus S is 2, L minus S is 0. So with an integer difference, you can write 2, 1, 0. Therefore, 2s plus 1 Lj can have three possibilities, 3p2, 3p1, 3p0. Why it is p? Because L is equal to 1. Whenever you have L equal to 1, you have to write p. When S equal to 1, 2s plus 1 becomes 3. So 3p2, 3p1, 3p0. The terms are 3p2, 1, 0. It is actually 3 terms. When S equal to 0, L equal to 1, J have only one possibility, 1, and the term is 1p1. The total spectroscopic terms are 4. 3p2, 3p1, 3p0, 1p1. Okay, for an sp electron. Now you can consider the case with one electron excited to d orbital. that is one electron in the S, one electron in the D. It is known as SD electrons. So S1 equal to half, S2 equal to half, capital S can be 1 or 0. L1 is 0, L2 is 2, capital L can be, can have only one value 2. The possibilities are S1 and L2, S0 and L2. Okay, so with the S1 and L2, J can have values 3, 2, 1. So the term is 3D. Why it is D? Because L value is 2. 3D, 3, 2, 1. When L equal to 2, S equal to 0, it is 1D2. J have only one value. So a triplet, this is known as a triplet, and this is a singlet. Okay, so when you have two electrons, one in S and one in D, the possible spectroscopic terms are a triplet and a singlet. And now one electron excited to F orbital. One in S, one in F. S1 is half, S2 is half, S is 1, 0. So whenever you have two electrons, the excited state always have two possibility, S equal to 1 and 0. What about L? L have only one possibility, 3. So with the S1 and L3, you will get a triplet, 3F, 4, 3, 2. This 4 is simply, F means L value 3. Here 3 means S value 1. So 3 plus 1, 4. 3 minus 1, 2. So with an integer difference, you can write 4, 3, 2. And with S equal to 0, L equal to 3, it will be 1 of 3. Again a triplet and a singlet. So you can continue like this. One electron in S, the other electron in P, D, F, G, etc. You will get a triplet and singlet like this. Now, suppose both electrons excited to P. Okay, both electrons are excited and they reach the P orbital. That is, you have now two P electrons, PP electron. Okay, you can denote it as PP electrons. Then S1 is again half, S2 is half, depending on whether it is in the same direction or opposite. You can have capital S1 or 0. L1 is now 1 because both electrons are P. L1 is 1, L2 is 1. So capital L can be L1 plus L2 to L1 minus L2, that is 2, 1, 0. 2, 1, 0. Okay. So S is equal to 1, you consider this case, S equal to 1, L equal to 2. Then S equal to 1, L equal to 1. S equal to 1, L equal to 0. S equal to 0, L equal to 2. S equal to 0, L equal to 1. S equal to 0, L equal to 0. There are 6 possibilities. The first one, S equal to 1, L equal to 2. J values. J can take values mod L plus S to mod L minus S. That is 2 plus 1 to 2 minus 1. So 3, 2, 1. S equal to 1, so it is a triplet. L equal to 2, so it is a D term. 3, 2, 1. So 3D, 3, 2, 1. S1, L1, so 3P, 2, 1, 0. S1, L0, so this 3S1. Now with the S equal to 0, they are singlets. And depending on the L value, you can have D, P or S. 1D2, 1P1, 1S0. Okay, these are the possible spectroscopic terms for two P electrons. Suppose one electron is in P and the other one is in D. Okay, in an excited state, you can consider one electron at P and one electron at D, and it is PD electron. Again, S1 half, S2 half, S equal to 1 or 0. L1 equal to 1, L2 equal to 2. Capital L is 3, 2, 1. Okay, so you can write the 6 possibilities like this with S1, L3, S1, L2, S1, L1. Then S0, L3, S0, L2, S0, L1. These are the 6 possibilities. For S equal to 1, L equal to 3, J can have values 4, 3, 2. For S equal to 1, L equal to, J can have values 3, 2, 1 and so on. So the terms are 3F, 4, 3, 2, 3D, 3, 2, 1, 3P, 2, 1, 0. Okay, whenever you have S equal to 1, it will be a triplet. Whenever you have S equal to 0, it will be a singlet. So these are the spectroscopic terms, possible spectroscopic terms for a PD electron. Then I will summarize these things like this. If you have two S electrons in an excited configuration, it will be, the possible terms will be 3s1 and 1s0. 3s1 and 1s0. Already discussed. sp electron, that is already discussed. 3p, 210 and 1p1. sd electron, 3d, 321 and 1d2. sf, 3f, 432 and 1f3. sg. Okay, you can continue like this for any value. Okay, the one electron is in S, the other one is in S, P, D, F, G, etc. Okay, now suppose one electron is in P, the other one is in P, D, F, etc. Then the first case, PP electron, we already discussed, 3 triplets and 3 singlets. Actually, this S, even though the left top is 3, it is not a triplet. There is only one state. So, except for S, all the other P, D, F, G, etc. are triplets. When the left top number is 3, P, D, F, G, etc. are triplets. But S is not a triplet. Even though here it is 3, it is not a triplet, it is a singlet. And left top 1 implies it is a singlet. Okay, so 3D 321 is actually 3 states, 3P 210 3 states, 3S1 is simply a single state. So total here 3 plus 3 plus 4, total 10 states will be there. For 2 p electron, total spectroscopic times possible are 10. For PD electron, 3 plus 3 plus 3, 9 plus 3, 12. The total possible spectroscopic terms 12. PF again total terms 12. Okay. And coming to DD electron, DD. Okay. Then as usual you have to write capital S 1 or 0. Then 2s plus 1 will be 3 or 1. 3 or 1. What about capital L value? Since you have 2d electron, L1 is 2, L2 is 2. So capital L can be 4, then 3, 2, 1, 0. L plus S, sorry, L1 plus L2 to L1 minus L2. So 2 plus 2 to 2 minus 2. With an integer difference, you can write 4, 3, 2, 1, 0. For L equal to 4, you can have G. L equal to 3, you can have F. L equal to 2, you can have D. L equal to 1, you can have P. L equal to 0, you can have S. For all those, you will have S, capital S 1, capital S 0. So, a triplet and a singlet. Triplet, singlet, triplet, singlet for all the L values. So, total number of terms 4 plus 4 plus 4 plus 4, 16. And here S is not a triplet, it's a singlet. So, 3s1, 1s0. It will make 2. So, 16 plus 2, 18. Total number of possible spectroscopic terms 18. Coming to DF, L values are 2 and 3. So 2 plus 3, 5, 2 minus 3, 1. So 5, 4, 3, 2, 1. For 5, the notation is H, for G, 3F, 2D, 1P. The total number of spectroscopic terms 4 plus 4 plus 4 plus 4 plus 4, 20. Okay, so you can write the possible spectroscopic terms for 2 electron system for any of the configuration. All these are for excited state. Okay, ground state there is a unique term symbol. Excited state, the system can take any of this state. Okay, so these are the possible spectroscopic terms for systems consisting of 2 valence electrons. Okay, now there is an important concept known as equivalent electrons. What is the meaning of equivalent electrons? Electrons having same n and l values. Each electron can be specified by specifying principal quantum number n, azimuthal quantum number or orbital angular momentum quantum number L, then ms, ml, etc. Usually, we are interested in 4 quantum numbers n, l, ml, ms. And according to Pauli exclusion principle, no two electrons in an atom can have all these four quantum numbers the same. Okay. And if you have two electrons in an atom which is having the same n and l value, it is known as equivalent electrons. For example, if you consider an electronic configuration like this, here you can have electrons, but I am interested only in these two electrons. If these two electrons are in 2p state, then they are equivalent. And if the two valence electron, one is in 2p and the other one is in 3p, when the two electrons are excited such that one goes to 2p and the other goes to 3p, they are non-equivalent. If both electrons goes to 2p, then they are equivalent. And in the case of equivalent p electrons, you cannot have this much spectroscopic terms. There will be some restriction as per Pauli exclusion principle. If it is in 2p and 3p, the 2p electrons, one is in 2p and the other is in 3p, there is no problem. All these 10 spectroscopic terms are possible. But if you have two equivalent electrons, here these two are equivalent because both have the same n and l values, because principal quantum number n is 2, l is 1. ml is different, ms is different. Okay, ms is same, sorry, ml is different. Okay, any of the among the four quantum numbers, at least one should be different. That is Pauli exclusion principle. Okay, so when you have two equivalent p electrons, there will be some restriction for the spectroscopic terms. So what are the possible spectroscopic terms if the electrons are equivalent? That is the question. So how can we find that? That we will discuss now. Consider two equivalent p electrons. Suppose you have two equivalent p electrons. Now let's write their ml and ms values, possible ml and ms values. For each electron, since it is p electron, ml can have value 1, 0 or minus 1. Okay, since it is in a p orbital, this first shell or first column will have ml value plus 1, this is 0, this is minus 1. So electron can sit in any of this column. So ml value is 1, 0, minus 1. Also the electron can have an upspin or a downspin. It can sit with an upspin or a downspin. So it can have ms value plus half or minus half. So total there are 6 options. Electron can take ml plus 1, ms plus half, like this. ml plus 1, ms plus half. Electron can take ml 0, ms plus half, like this one. This is ml 0 and ms plus half. Electron can take ml minus 1, ms plus half. That is, if it is sit in this last column, then that will be ml minus 1, ms plus half. Also, it can sit in the first column with a downspin, that is ml1, ms minus half, then ml0, ms minus half, ml minus 1, ms minus half. These are the only 6 possibilities that a p electron can take. Okay, a p electron can take any one of these 6 possibilities. I will call these as A, B, C, D, E, F. So each electron will be in any of these 6 possibilities. And what is Pauli exclusion principle? It states that no two electrons in an atom can have all the 4 quantum numbers the same. That is, since you have 2 electrons, if one electron chooses possibility A, the second one won't choose A. If the first electron chooses A state, then the second electron will not choose A. It can choose B, C, D, E, F. It will not choose A because we are considering equivalent electrons. Already N value and L value are same. And if one electron chooses A and second also chooses A, ML and MS will also be the same. So that is all 4 quantum numbers becomes the same for both electrons. That is why if one electron chooses A, the second one can choose either B, C, D, E or F. Okay. So what are the combinations? If first electron chooses A, second electron can have B, C, D, E or F. So 5 possibilities. If first electron chooses B, then second electron can choose C, D, E, F. I will not write A here because BA and AB are same. Okay, no need to write again BA. So BC, BD, BE, BF. And the next 3 CD, CE, CF, DE, DF, EF. So these are the 15 possibilities for the 2 electron system. For a single electron, there are 6 possibilities. For 2 electrons, according to Pauli exclusion principle, there is only 15 allowed states. Okay, I will write the total ML and MS values for these 15 combinations. Total ML and MS values for these 15 combinations. For example, for AB, this combination, 1 electron in the A state, second electron in the B state. If 1 electron in the A state and second electron in the B state, what is the total ML value? For the first electron it is 1, second electron it is 0, so 1 plus 0, 1. Total MS value, half plus half, 1. So that is what we written here. ML, total ML value, total value is 1. MS is also half plus half, 1. For AC is 1 electron in this configuration, 1 electron in this configuration, sum of ML value 1 minus 1, 0, half plus half, 1. That is why here you have 0, 1. In a similar manner, you can write these quantities for the 15 cases. Okay. Now, in this, take the largest value of capital ML. Largest value of capital ML. In these 15 values, what is the largest one? It is 2. ML equal to 2 means it's a part of L value 2. Because if you have L2, possible ML values are 2, 1, 0, minus 1, minus 2. So ML, there is ML2 means it is from an L value 2. L value 2 means it is a D term. So this is actually a D term. If it is L value 1, it will be a P term. L value 3, it is a F term, like that. For L value 2, it is a D term. And for 2, what is the corresponding MS value? It is 0. For the largest ML, the corresponding MS is 0. MS is 0 means it is a singlet. Because MS actually capital S is equal to 0 means singlet, I already mentioned. And in my notation, capital S is simply the sum of MS values. Here it is MS is 0. The sum of MS values of individual electrons, it is 0. So it is a singlet. Therefore, L value 2, it is D term. MS value 0, it is a singlet. So the term is 1D2. And for 1D2, since it is a D term, there will be total 5 members. So the members are 2, 1, 0, minus 1, minus 2. This black boxes. This black box and this black box constitutes this 1D2 term. 2, 1, 0, minus 1, minus 2 with all MS equal to 0. So it is 1D2 term. Now you avoid these black boxes. Consider the remaining terms. Next highest ML value, if you avoid this box and this box, next highest ML value is 1. It corresponds to L value 1. Okay, ML equal to 1 means there will be an L value of 1. Because for L value 1, ML values are 1, 0, minus 1. Okay, so L value 1 means it is a P type. Now go to that ML1. What is the corresponding MS? It is 1. If MS is 1, it is a triplet. If MS is 0, it's a singlet. If MS is 1, it's a triplet. So the possible terms are 3P. L value 1 means P. Triplet means 3. So 3p210. J values, possible J values are 210. So this is a possible spectroscopic term, 3p210. So we have to mark this triplet, and that will be 1 0 minus 1 with 1, this box and this box, 1 0 minus 1 with 1, 1 0 minus 1 with 0, 1 0 minus 1 with minus 1. Triplet means there should be 3 such terms, 1 0 minus 1 with 1, 1 0 minus 1 with 0, 1 0 minus 1 with minus 1. This is the triplet type. So the only remaining thing is this 0 0. So the ML value is 0, so it corresponds to S time. MS value is also 0, so it is a singlet, so that is simply 1s 0. So what are the possible terms? 1d2, 3p210 and 1s 0. Okay, so as per Pauli exclusion principle, for two equivalent p electrons, so for two equivalent p electrons, we can have only 1d2, 3p210 and 1s 0 times, total 5 times. This is 1, this is 3 times, this is 1, so total 5 times. If they are not equivalent p electrons, then we have how many possibilities? These two equivalent, if they are non-equivalent p electrons, we can have triplet D, singlet D, triplet P, singlet P, then 3s1, 1s1, pp electrons. Okay, triplet D, singlet D, triplet P, singlet P, triplet S, it is not a triplet, 3s1 and 1s 0. Total 10 times will be there if you have two non-equivalent p electrons. But if it is equivalent p electrons, then the terms 5 times will be excluded. Now I will explain an alternate method in order to find the possible spectral terms or spectroscopic terms in the case of equivalent electrons, because this procedure is a little bit difficult in order to find the possible spectroscopic terms for equivalent electrons. This is not much difficult because it is 2p electron. When you have 2d electrons, the possibilities will be 10 and the combinations will be 45 and so on. So it will be very difficult. So I will give you an alternate method, and that is known as Briet scheme, in order to find the possible spectroscopic terms for two equivalent electrons. Again, I will explain by considering examples. You consider two equivalent p electrons, and you have to form two squares. One is known as ml square, the other one is known as ms square. How can we write the square? You write the ml values of first electron in a horizontal manner and the second electron in a vertical manner in the same order. Since you have two p electrons, the first electron is a p electron, so you write the ml values 1 0 minus 1 horizontally. For the second electron, you write it in the same order but vertically, 1 0 minus 1. Now you can form a square table. The entries of this square table is obtained by adding the corresponding ml values. For example, this entry is 1 plus 1. This is 1 plus 0. This is 1 minus 1. Hence you can fill all the positions. So you obtained ml square table. In a similar manner, ms. For the first p electron, ms can have half or minus half depending on upspin or downspin. Second electron also have two possibility, half and minus half. Again, this entry is half plus half. This is half minus half. Okay, so these entries are obtained by adding the respective values. So you have two squares. One is ml square, the other one is ms square. Okay. You are considering equivalent electrons. N and L already same. Okay. N and L already same for the two electrons. Now suppose you are considering the diagonal position of ms square. What is the meaning of diagonal position of ms square? Both electron have same ms value. same ms value, then only you will get the diagonal position, because if two electrons are up spin half, then you will get this position. If both are in the down spin, you will get this position. So diagonal of ms means you are taking both electron the same ms value. Then already n and l same, now ms are also same. But according to Pauli exclusion principle, no two electrons in an atom can have all the four quantum numbers same. Already three are same. Then ml should be different. So you have to avoid the diagonal positions of ml square, because diagonal position of ml square means both electrons have same ml values. Okay, now the electrons have same n, same l and same ms, because we are considering the diagonal position of this ms square. Then you have to avoid the diagonal position of ml square. When you take the diagonal position of ms square, then you are taking total ms value as 3. Sorry, total ms value as 1. Then the term symbol 2s plus 1 lj, the 2s plus 1 value will be 3. Okay, when both electrons are in the upspin or downspin, then total s value is 1. We are considering only modulus. So total s value 1 means 2s plus 1 value is 3. So when you are considering the diagonal position, it is actually a triplet. Then you have to write 3 here. Then what is the corresponding L value? L value, you cannot take the diagonal positions. Then the remaining is 1, 0, minus 1. This combination, 1, 0, minus 1. 1, 0, minus 1 is a part of P term. So you have to write 3P. 3P. 3P, what are the possible J values? When S is equal to 1, L equal to 1, J value is 2, 1, 0. So once you have 3P, you can write the J values 2, 1, 0. So this is one of the possible spectroscopic term. Then this is the only one with a triplet. Now you have to consider the off diagonal position of ms. That is ms equal to 0, s equal to 0. So 2s plus 1 becomes 1. That is a singlet. What are the possibility for here? When you are considering off diagonal position here, that is you are taking different ms values. Then you can take same ml value, that is you can consider the diagonal position. When you consider the diagonal position, this is 2, 1, 0, minus 1, minus 2. So it is a part of D term, and the other possibility is 0. So it is a S term. So 1D and 1S. J value you can of course write as 2 and 0. Because S is 0, J is simply L. Since it is D, L value is 2, so J value is 2. So 1D2, 1S0, 3P, 210. These are the possible spectroscopic terms for equivalent P electrons. This is exactly the same we obtained in the previous case also. Okay, so this is a different method. Here you just write the ml square and ms square, then consider the diagonal position of ms square, and that will be triplets. Then you have to avoid the diagonal position of ml square. Take the remaining ones. Then when you take the off diagonal position of ms square, consider the diagonal position of ml square. And you can write both triplet and singlet. Okay. I will give you one more example. Two equivalent d electrons. For the first electron, you have to write it in the horizontal manner. Second electron, you have to write it in the vertical manner. Since it is a d electron, ml value is 210 minus 1 minus 2. Similarly, 210 minus 1 minus 2. Fill the square by adding the respective position numbers. So you will get this one. Corresponding ms square, half minus half, half minus half. It is always the same. For 2 electron case, ms square is always the same. Consider the diagonal of ms square. That is triplet. So you have to write 3. Then you have to neglect the diagonal of ml square. Take the other things. 3, 2, 1, 0, minus 1, minus 2, minus 3. So it is a part of f term. Then 1, 0, minus 1. 1, 0, minus 1. It's a part of p term. So triplets, you have two possibilities, 3f and 3p. Of course, you can write the j value here. Okay. For 3f, the only possible j values are 432. 3p, the only possible j values are 210. These are the two triplets possible. Now, when you are considering off diagonal position, you have to write 1 because it is a singlet. Then you can consider this diagonal. Starts from 4 to minus 4, 2 to minus 2, 0. 4 is G term, 2 is D term, and 0 is S term. So 1G4, 1D2, 1S0. These are the possible spectroscopic terms for equivalent d electrons. There are only 9 possibilities. If they are non-equivalent d electrons, we have 18 possibilities, and when you have to consider the Pauli exclusion principle, 9 of them will be excluded. 9 of them will be excluded. Now consider the case of 2 f electrons. 2 f electrons. For the first f electron, you can have ml values minus 3, minus 2, minus 1, 0, 1, 2, 3. For the second electron, you have to write it in the vertical manner. Minus 3, minus 2, minus 1, 0, 1, 2, 3. Make this square, ml square. Make the ms square. Take the diagonal of ms square. That is a triplet, because total s value is total ms value is 1. So it's a triplet. Then you have to neglect the diagonal of ml square. The remaining is minus 5 to plus 5. That is simply an h term. Then minus 3 to minus 3 f term. Then minus 1 to 1 p term. So 3h, 3f, 3p. J value 210, 432. H means L value 5. This is S value 1. 5 plus 1, 6. 6, 5, 4. Okay, these are the triplets, possible triplets for 2 equivalent f electrons. Now singlet. You are considering off diagonal ms, different ms values for electrons. So you can consider the diagonal position of ml. So there are minus 6, minus 4, minus 2, 0. Okay, 6 means I, 4 means G, then 2 means D, then S. So 1I, 1G, 1D, 1S. They are respectively 6, 4, 2, 0. The possible spectral terms are 9 plus 4, 13. 9 plus 4, 13. If they are non-equivalent f electrons, then the total possibilities will be 26. When they become equivalent, Pauli exclusion principle excludes 13. Excludes 13 terms. The possible terms are now only 13. Otherwise, it will be 26. I think now it is clear, the Briet scheme. Okay. You make ml square and ms square, then consider the diagonal of ms, then don't consider the diagonal of ml square, because otherwise both will have the same ml and ms values. Already they are equivalent means they have the same n and l values. Okay, all 4 quantum numbers cannot be the same for 2 electrons. Okay, again this Briet scheme was also a little bit difficult. I will give you an alternate third procedure to find the possible spectroscopic terms. When you are writing a competitive exam, you can use this method in order to find what are the possible spectroscopic terms for equivalent electrons. For 2p electrons, equivalent to p electrons. In this method, what you have to write is the total ml value horizontally and total ms value vertically. Whether it is 2p electron or 2d electrons or 2f electrons, all have the ms combination same 1 and 0. Okay, because s values are half and half, so the combination can be either 1 or 0. So this position is always the same. What about this position? In order to find the horizontal one, if it is 2p electrons, one of the p electron mean L1 is 1, L2 is 1, both are p electrons. So total L value is 2, 1, 0. 1 plus 1, 2, 1 minus 1. So you have to write it on the horizontal position. 2, 1, 0. If it is 2 d electrons means L1 is 2, L2 is 2. Total L value can be 4, 3, 2, 1, 0. You have to write it here. 4, 3, 2, 1, 0. And for 2f electrons, f means L equal to 3. 3 plus 3, 6. 3 minus 3, 0. 6, 5, 4, 3, 2, 1, 0. Okay, this is the way in which you can write the horizontal position. Vertical position are always 1 and 0. Now, ms or total s is 1 means it is a triplet. It's a triplet. Okay, so you have to write 3 here. Depending on the value of L, you have to write D, P, S, these symbols. For L equal to 2, you have to write D. L equal to 1, you have to write P. L equal to 0, you have to write S. L equal to 6, you have to write I. L equal to 3, you have to write F. L equal to 4, you have to write G, and so on. Okay, depending on the value of L equal to 0, S, 1, P, 2, D, 3, F, 4, G, 5, H, 6, I, and so on. Okay, that is the manner in which you filled this. For S equal to 0, that are singlets. Okay, so this is the method in which you can find the spectroscopic terms for 2p electrons. All the 6 are, these are not actually 6. This 3D means you can write 321 J value, here 210. So this is 3 plus 3, 6, and this is a single level, 3s1, and 3 plus 3, 6, plus 4, 10. Total 10 spectroscopic terms are possible for 2p electrons. When they are equivalent electrons, you have to exclude some of them. Okay, you have to consider only these circled ones. What is the peculiarity of these circled ones? For circled ones, both ms and ml are either even or odd. When you are considering ms is equal to 1, you have to consider only the odd ml value, that is this position, not consider this one or this one. When you take ms as 0, that is even, you have to consider ml also as even. Okay, when you consider odd ms, you consider odd ml only. When you consider even ms, you consider even ml only. That are the possibilities when they are equivalent p electrons. When they are equivalent d electrons, the possibilities are when you take ms as 1, you take ml as 3 or 1, odd ones only. When you take ms as 0, take even mls. These are the possible spectroscopic terms. If they are non-equivalent, all these are possible, but for equivalent electrons, only the circled ones are possible. Similarly, for equivalent f electrons, when you take ms is equal to 1 triplet terms, you have to consider only 5, 3, 1, odd ones, 5, 3, 1. When you take 0, you have to consider only the even terms, 6, 4, 2, 0. So these are the possible spectroscopic terms for equivalent. Okay, the circled ones are the only possible ones for equivalent f electrons. I think this is the most easier method in order to find the total spectroscopic terms as well as the spectroscopic terms for equivalent electrons. Okay, so here you can see that only this S is, even though the left top is 3, it is not a triplet, it is a singlet. All other P, D, F, G, H, I, all are triplets when the left top is 3. 3 possibilities, 3 possible J values are there. When the left top is 1, they are singlets, only one J value is possible. Okay, so this is all about the possible spectroscopic terms for systems having 2 valence electrons. There is always a triplet and a singlet, and this is the method in which we can find those terms. Okay, thank you.